Hello, fellow problem solvers. So they're going to be doing a problem from the Elmo 2016 problem number 1. I really like Elmo. I've said it before and I enjoy this problem. I remember doing this when I was preparing for the 2016 IMO. It's a beautiful problem. I mean, it's a cute little problem. So it has a little extra thing about the crunchy monster, cookie monster. It has something about the cookie monster. That didn't have anything to do with the problem, so I didn't write it down. Anyways, I don't get that. Like, why the cookie monster? It's a combination of memes and mathematics. I try to keep them separate. So, I invite you to try this problem out for a minimum of 10 minutes, ideally half an hour to maybe 45 minutes, not more than an hour and a half. If you'd like to go along with us, give it a go for 15 minutes. And here's the first step. So, we have that. Let's see what needs to hold true. The sum of any and xi's equals the product of the remaining xi's. Okay, so let's write this down though. So this is, for example, x1 plus x2 plus xn is equal to the product of xn plus 1 till xn 2n. Right? And this holds true, like we can switch these around. Now, the first idea for me was, well, let's see if I just move this by 1. So if I just switch x1 and xn minus 1, the same thing needs to hold true. Xn plus 1 plus x2 plus xn is equal to x1, xn plus 2 all the way till x2n. Let's call this thing P. Let's call this sum S. It's just simpler that way. Like, life is a lot simpler that way. And we have that here. We have x1 plus s is equal to p xn plus 1, and xn plus 1 plus s is equal to p x1. Right? So now from here, we can look at this as a quadratic is one thing. I just want to subtract. Subtraction, when you have two things like this, which are kind of, I don't think it's symmetric is the term. Maybe it's symmetric. Symmetric or cyclic. You want to subtract and see what you get. Like, sometimes subtraction is much better than taking x1 is equal to pxn minus s and then putting it here. Because then you have a higher degree problem. You have a degree of p, you have xn plus 1 in p. Sure, it tells you something. I mean, it tells you you'll still get the same thing, I think, but I usually go with subtraction. When we subtract, we have x1 minus xn plus 1 is equal to p times xn plus 1 minus x1. Wow, this is similar. Move it to the other side, and we get x1 minus xn plus 1 times p plus 1 is equal to 0. Because this, if we move it here, it's just going to switch sides. Like x1 and xn plus 1 are going to switch sides. And we have this is true. This is, mind you, true for any x1 and xn plus 1. Now, here's where I invite you to pause for 10 minutes and see how you can push the problem further. And here's the next step. So, what this really tells us is that, mind you, not all of them can be equal. And this tells us that for any two, x1 and xn plus 1, the two of them and the product of the remaining, of any actually, this is not the product of any remaining n minus 1, right? We pick these n minus 1. But if we switch these numbers aside, we would have the other n minus 1 numbers. So this tells us that either for every two numbers, they are the same, or we have that the product of the rest of them, of any n minus 1 of the rest of them is equal to minus 1. Now, here's where I invite you to pause for the next 5 minutes and push the problem further. And here's the next step. And the next step is, so now we need to have at least two of them which are different. Assume x1 and x2 are different. So in that case, assume x1 and xn plus 1 are different. It doesn't really matter. Then we have that the product x. Actually, let's just assume x1 and x2 are different, right? And then we can pick any other ones like x1 isn't equal to x2. Or actually, x1 isn't equal to x2n. I like it more. It doesn't really matter. I'm just doing this for myself. So here, these two are different. That means that the product of any other n minus 1 is going to be equal to negative 1. So I'll have that x2, x3 till xn plus 1, or actually till xn is going to be minus 1. And also x2, x3 till xn minus 1, xn plus 1 is also negative 1. Now, none of these are 0, so we can divide. And what we're left with is that these two, actually we can equalize them. And then that gives us that xn is equal to xn minus 1. So now we have, of the remaining n minus, like mind you, these are arbitrary two numbers that I picked. So now we can have we have these two are not equal to each other. And then and then all the other numbers, if I pick any two pairs, they're going to be equal. So this means that this sequence needs to be of the form A, B, and then C, 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 C. Now, because I can also have either A or B isn't equal to C. If A isn't equal to C, I take these two as my x1 and x2n here, and then I'll have B is equal to C, because I'll do the same thing. I'll have B, C, 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 C is equal to negative 1, and then C, 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 C is equal to negative 1 for different, like this is going to be, actually I messed up my ordering, but it doesn't, like the substance matters here. So like the big idea here. So we have, the sequence needs to be of the form A and all C's, and now it also needs to satisfy this. So the sequence is necessarily this. Now, this also means that the product of any n of them needs to be negative 1. Actually, the product of any n minus 1 of them needs to be negative 1. So the product of C, actually not the product of any n minus 1 of them, but if I pick A and C, then the product of any n minus 1 C's must be negative 1, because for the other two we'll have, if I pick a C and a C, this will be 1. So now we have C to the n minus 1 needs to be equal to negative 1. Given these numbers are real, this means that C in fact needs to be equal to negative 1, and n minus 1 needs to be odd. In other words, n needs to be even. So only even n can satisfy this. Like the odd n cannot satisfy this. And now for the final step is to show, like we've shown that n needs to be even. And now the next part is showing that if n is even, we can find numbers which satisfy this. And here's where I invite you to pause for another 5-10 minutes and push the problem further. And here's the next step. So the next and final step is, what do we have? We had here x1. Let's just take 2. So when we sum up all the c's, we sum up all the c's, we'll have c plus c plus c. If we have c's summed up, is equal to c to the n minus 1 times a. And if the a is on these summers, sum up side, we'll have a plus c plus all the way till c. N minus 1 c's, here we're going to have n c's, is equal to c to the power of n. So now, let's see what we have here. This thing right here, c to the power of n, is going to be 1. And this is going to be minus a because n is even. What is this? This is going to be equal to minus n. So a is going to be equal to minus n, which means a is equal to n. And then a minus n minus 1 is 1. So the sequence which satisfies this is 1, n minus 1 minus 1 minus 1, and all minus 1s. And it works. So even n work, odd n do not, and this finishes up our problem. And this is why I think it's a cute problem. You just like switch two numbers. You see what happens if I have x1 through xn, and then x1, and then say x2 through xn plus 1. You see, oh, this gives me either that numbers are equal, or the product of the n plus 1 is minus 1. But then you see, wait, this means this is really, I can pick any two numbers. And the product I can make any other n minus 1 numbers, I can make it in the product. And you realize those two things, and the problem then just flows, opens up. This is why I think this problem is useful to like help thinking, why I like the Elmo a lot, is this sort of thinking is very much competitive mathematics, right? There's not any major theory that you're using, you're just taking it step by step by step by step and solving it. And as always, thanks for problem solving.